So now we move on to talking about infinity. So the idea of infinity is it is the extreme on how large a number can be. It is not a real number. For one thing, believe it or not, infinity plus 1 is infinity. 3 times infinity is infinity. Actually, for that matter, any number greater than 0 times infinity is infinity, and any number less than 0 times infinity is negative infinity. So it does not behave like a real number because a lot of the operations don't do what they otherwise would. Now, where it has an application and where we are interested is when it comes to graphs and extreme values. So when we look at this graph right here, think about it. Before I go over it, where would x going to infinity, where would that be on this graph? Also think about where would x going to negative infinity be on this graph. So if we look at this graph, x going to infinity is on the far right. So if we were to go over to the right forever, this would be over where x approaches infinity, if we were to go forever there. Now, what does this graph appear to be headed towards as you go to the far right? Again, I'm going to pause. So this graph would appear to be headed towards 2. Now, as it turns out, this is specifically selected function where, yes, the graph will get closer and closer to y equals 2 as x gets really large. And what this means is that the limit as x approaches infinity of this function is 2. So when it comes to calculating infinite limits, a key idea is the limit as x approaches infinity of 1 over x. And because infinity is a really large number, we can think of this as a progression of what happens as a number gets really large with regard to a function. So to do this, we can take a progression. In this case, we're going to put inputs of 5, 10, 100, 10,000, and then 1,000,000 into the function 1 over x. And we're going to look for a pattern to see what is happening to these numbers. So if we plug in x equals 5, we get 1 over 5, which is a decimal, is 0.2. If we plug in 10 for x, we get 1 over 10, which as a decimal is 0.1. If we plug in 100, we get 1 over 100, which as a decimal is 0.01. Then if we plug in 10,000, so that's 1 over 10,000, which as a decimal is 0.0001. And then similarly, 1 over 1,000,000 would be what we would get for plugging in 1,000,000, and that would be 0 and then 5 zeros. Now, think to yourself, where are these numbers headed? What is happening as the input gets larger and larger? So, looking at this table, these numbers are getting closer and closer to 0. And in theory, if we were to get larger and larger, we continue to get closer to 0 to the point where the difference would become negligible. The difference for 1 divided by a very large number, it's almost 0. So we say the limit as x approaches infinity of 1 over x is 0. And more specifically, we can say that any number, and this does not include infinity, divided by infinity will equal 0. So even if you take 7 billion and you divide it by infinity, it's 0. Now, let's take a look at the two limits below. The limit as x approaches infinity of 1 over x squared, and the limit as x approaches infinity of 1 plus 3 over x. So, for the limit as x approaches infinity of 1 over x squared, think about it this way. I could rewrite this limit as the limit as x approaches infinity of 1 over x times the limit as x approaches infinity of 1 over x. Because 1 over x times 1 over x is 1 over x squared. Well, doing that would give me 0 times 0, which is 0. And as a matter of fact, we can go further to say that the limit as x approaches infinity of 1 over x to the nth power is 0 whenever whenever n is any positive real number. So whenever n is 1, 2, 3, going on up, any positive integer, 1 divided by x to that power, it's going to be 0. Now, if we look at the second limit, we could rewrite this, because with regard to limits, you can rewrite the limit of a sum as the sum of two limits. So this becomes the limit as x approaches infinity of 1 plus the limit as x approaches infinity of 3 over x. Well, so first of all, there isn't a variable in this first limit. So because there is not a variable in this first limit, it's just equal to the number that it is. Now, with regards to the limit as x approaches 3 over infinity, we use the idea that any number divided by infinity is 0. Well, so that means that 3 over infinity is equal to 0. And so, this second limit is just 0. And so our answer to this problem would just be 1. And this is a key idea, and that is if you're adding and you have a number plus a number over infinity, the number over infinity is 0. And so we're just left with whatever is not divided by infinity. So now, let's utilize these ideas to calculate some more complicated limits involving infinity. Okay, so when it comes to calculating infinite limits of rational functions, by the way, just to be clear, a rational function is any function that can be written as a fraction. Our general method is that we are going to divide by the highest power of x on the bottom. That is, we're going to divide the top and the bottom. So I should be a little more specific. So I'll say divide top and bottom. So we're going to divide the top and the bottom, or in other words, the numerator and denominator, to be more formal, by the highest power of x on the bottom, and then we're going to plug in infinity. So if we look at this first limit right here, the highest power of x on the bottom is x to the third. So we're going to divide the top and bottom by x to the third, which dividing is the same thing as multiplying by 1 over, so that means multiply the bottom by 1 over x to the third and multiply the top by 1 over x to the third. So this is the same idea as you used a long time ago when you simplified fractions. So doing this, so we distribute the 1 over the x to the third to everything. So now we have limit as x approaches infinity of 5x to the third over x to the third minus 5x over x to the third plus 1 over x to the third over 4x to the third over x to the third plus 9x squared over x to the third. So now we can simplify this a little bit. So the 5x to the third over x to the third, the x to the thirds are going to cancel out, and we're just going to be left with 5. For x over x to the third, that x is going to cancel out with one of these, and we're going to be left with, actually, so it's minus 5 over x squared. And then there's nothing we can do with the 1 over x to the third, which is 5. And then similarly on the bottom, so 4x to the third. So 4x to the third divided by x to the third, the x to the thirds cancel out. And then 9x squared over x to the third. 2 of the 3 x's on the bottom are going to cancel at the top, and we're going to be left with 9 over x. So the bottom becomes 4 plus 9 over x. Now we can plug in and note that infinity to any power where n is 1, 2, 3, and on up. So infinity squared, infinity cubed, infinity to the fourth, etc. is just infinity. So this means this limit becomes 5 minus 5 over infinity plus 1 over infinity. And then the bottom becomes 4 plus 9 over infinity. So that then becomes 5 minus 0 plus 0 over 4 plus 0. And so our final answer is 5 over 4. And this is the general method that we can use for any problem of this type, where we have the limit as x approaches infinity of a rational function. So with that in mind, for the next problem, the limit as x approaches infinity of 4x squared over x cubed minus 1, we do a similar process. The highest power on the bottom is x to the third. So we multiply again by 1 over x to the third on the bottom and on the top. So this gives us the limit as x approaches infinity. And so the top is going to become 4 over x, because two of the 3 x's are going to cancel. The bottom is going to become 1 minus 1 over x to the third. So plugging in, 4 divided by infinity is 0. And then we have 1 minus 0 on the bottom, because infinity cubed is 0, and 1 divided by infinity is 0. So this is 0 over 1, and if you think about it, 0 cupcakes divided by 1 person, you get 0 cupcakes. So it's 0. And that's your answer. Okay, a couple more examples. In part also, I want to show you all the varieties of this. So now, with problem 3 of this set, on the bottom, our highest power of x is just x the first, or x. So in this case, we're going to multiply the bottom and the top by 1 over x. So now, the top is going to become 4x squared over x. So one of the two x's in the x squared cancels, and we're left with 4x on the top. Then the bottom is going to become 3 minus 1 over x. So now plugging in, we get 4 times infinity over 3 minus 0. Well, 4 times infinity is just infinity, and 3 minus 0 is 3. Now, infinity divided by any number is infinity. So this becomes just infinity, and that's our answer. So some of these limits will result in an answer of positive infinity or negative infinity. Because by the way, if I put a negative sign out in front of this, it would be negative infinity. And then I'm going to show the last one, problem 4, as an example of another scenario. I'm not going to ask you any of these on homework or on a quiz because it's a little bit awkward. However, and actually there is another way of doing this that you will learn when you come back from Thanksgiving break. However, at least this way you can see it if you ever see somebody else doing this a certain way. So, first of all, think to yourself, how is problem 4 significantly different than the other 3? So hopefully, in looking at that, you saw the square root on the top. Now, we're still going to divide by the highest power on the bottom, so we're still going to multiply by 1 over x squared. However, that doesn't do us a whole lot of good on the top, except for we can note that x squared is equal to the square root of x to the 4th. So multiplying by 1 over x squared is the same thing as multiplying by 1 over the square root of x to the 4th. So we can do this, and what this also allows us to do is, because we're multiplying by a square root, so multiplying or dividing a square root by a square root means we can bring whatever is inside the square root inside the other square root. So we can distribute this x to the 4th to each of these things in here. So doing so, we have the limit as x approaches infinity, square root 25x to the 4th divided by x to the 4th. Make that square root a little bit larger. Plus 2x squared divided by x to the 4th. Plus 11 divided by x to the 4th. And on the bottom, we have 3x squared divided by x squared plus 7x divided by x squared. So now, we can go ahead, reduce things, so it still is a limit. So we got the limit as x approaches infinity. So the top is going to become the square root 25 plus 2 over x squared plus 11 over x to the 4th. The bottom is going to become 3 plus 7 over x. So then, plugging in infinity and noting that any number divided by infinity is 0, this gives us the square root of 25 plus 0 plus 0 over 3 plus 0. So 25 plus 0 is 25. The square root of 25 is 5. And then the bottom is 3, and you could leave as a fraction, or you could rewrite this as 1.67. So that's a general way of calculating limits involving infinity being plugged in. Another scenario comes up when a limit is actually equal to infinity. So to preview this scenario, let's take a look at two functions. Let's take a look at 1 over x minus 3, looking at a table as we go towards 3, and then let's look at 1 over parentheses x minus 3 squared, and again a table as we approach 3 from each side. So first of all, plugging in 2.5 for x gives us 1 divided by 0.5, because 2.5 minus 3, actually 1 divided by negative 0.5, as 2.5 minus 3 is negative 0.5. This results in negative 2. Similarly, plugging in 2.9, 2.9 minus 3 is negative 0.1, and so that results in negative 10. By a similar process, 2.99 results in negative 100. Now, for plugging in 3, this results in 1 over 0, which for right now we're going to say does not exist, as 1 over 0 is undefined when we're talking about graphing a function. And moreover, we're going to find out going the other way on this table that there's a bit of complexity in how 1 over 0 ends up being. So I realized early in the course I may have said some things about this. However, we're going to talk more in depth during this lesson. Okay, so I'm going to go the other way. I'm going to start from 3.5. So here, for x is 3.5. If I plug in 3.5 minus 3 is 0.5. And then 1 divided by 0.5 ends up being 2. Similarly, 3.1 minus 3 is 0.1. And then 1 divided by 0.1 is 10. And a similar thing happens with 3.01. So now I want you to think to yourself, where are we headed if we're going from the left and we're going towards 3? And then where are we headed if we start at the right and we go towards 3? And before we answer this one for this function, I want to do another one because this might solidify some of your thoughts on it, even though this is a little bit different. So, similar process here. We're making a table around 3, but this time it's 1 over x minus 3 in parentheses squared. So we'll see the effects this has. So plugging in 2.5, we get 1 over negative 0.5 squared. It's 2.5 minus 3 is negative 0.5. Now, squaring a negative number results in a positive number, so this is equal to 1 over 0.25, and it's positive, because again, a negative times a negative is a positive. So, 1 divided by 0.25 is 4, and again, that's a positive 4. Similar result happens if we put in 2.9. So 2.9 minus 3 is negative 0.1. Negative 0.1 squared is positive 0.01. And 1 divided by that is 100. And then for 2.99, plugging in, we end up getting positive 10,000. And again, for 3, it's 1 over 0 squared is just 0, and we represent this with does not exist. Because again, when it comes to graphing a function, the value does not exist at 3. There's nothing we can put on a graph at x equals 3 for that function. Going the other way, it's a similar pattern. 3.5 minus 3 is 0.5. 0.5 squared is 0.25. 1 divided by 0.25 is 4. And then for 3.1, it ends up being the same as it was on the other side. It's a 100. And 3.01 ends up being 10,000. So now, let's use this to calculate some limits. So, if you remember from earlier, there are two limits that we can do for a function. We can do the limit as x approaches a number from the left. So in this case, x approaches 3 from the left. And if we look at this function approaching from the left, it is getting more and more negative. And as it turns out, if we kept going, it would continue to get more negative. So this is equal to negative infinity. Now, specifically, if we were to take 2.999 ... minus 3, we would get negative 0.00 and eventually a 1. So we tend to call this 0 with a negative sign. This means it's almost 0, it's just slightly negative. And moreover, 1 divided by 0 with a minus sign is negative infinity. Now, if we look at the other side limit, if we look at the limit as x approaches 3 from the right, if we start here, we are getting larger and larger. And that pattern continues forever. So if we take the limit as x approaches 3 from the right of 1 over x minus 3, this is equal to positive infinity. And similarly, we can define 3.00 going on forever, 1 minus 3 being equal to 0.00 going on forever and then 1, which is just slightly positive even though it's almost equal to 0, and so we call this 0 with a plus sign. And as the limit as x approaches 3 from the right illustrates, 1 over 0 with a plus sign is equal to positive infinity. By the way, just to be clear, this is not a formal mathematical definition. This is a convenient computational technique. So all you mathematicians out there, if you see this, sorry, I'm not being completely formal. However, for an introductory calculus course, this gets the job done. Okay, so now if we take a look at these two limits, this is the left and right hand limit. Think about, what does this mean for the limit as x approaches 3, the two-sided limit of 1 over x minus 3? I'll pause for just a second. Well, more than a second. Okay, if you remember from earlier in the course, in order to have a two-sided limit exist, the one side of the limits have to be equal. In this case, the one-sided limits are not equal. And so this two-sided limit does not exist. Now, let's do a similar thing for g of x. So, for g of x, on the left, I'm going to erase some of this stuff to give myself some more room. Okay, if we take a look at the limit as x approaches 3 from the left of 1 over x minus 3 squared, we start at, so coming in from the left, we're at 4, then we're at 100, then we're at 10,000 as we get closer to 3. So not only are we positive, but it's getting more positive at a very rapid rate as we approach 3. And similar to the other one, this continues. And so here, this limit is positive infinity. Now, noting that with this idea down here, so if we were to plug in 3 with a minus, this limit would become 1 over 0 with a minus squared. Well, think about it. What is a negative number squared? Negative number squared is positive, so this becomes 1 over 0 with a positive sign, which gives us positive infinity. We get a similar result if we do the limit as x approaches 3 from the right. As going from the right, we're at 4, then we're at 100, then we're at 10,000, and we're increasing rapidly as we approach 3. And so the limit as x approaches 3 from the right of 1 over x minus 3 squared is positive infinity. Now, in this case, we have agreement. Both the limit from the left and the limit from the right are equal to infinity. And so the limit as x approaches 3 of 1 over x minus 3 squared is positive infinity. Okay, so let's practice these concepts on a few problems. So if we look at the first problem, we get the limit as x approaches 5 from the left of 1 over x minus 5. Well, given that it's 5 from the left with that minus sign, this is slightly less than 5. So for that reason, approaching 5 from the left for x minus 5, the denominator is going to be slightly less than 0. So this would be 1 over 0 with a minus. So now, positive divided by a negative is a negative, and 1 over 0 goes to infinity. So this becomes negative infinity, and that's our answer for this limit. Now let's take a look at the second problem. First of all, quickly think to yourself, how is the second problem different than the first problem? And what might this have, or what might this do to the results? So, first of all, as a general rule with just computing limits, we are going to plug in. Now, the thing about the top is this remains infinitely close to 2, what we're plugging in. Limit as x approaches 2 from the right is just about 2. So really, the top is going to be, so 2 minus 3 is negative 1. The top is going to be just about negative 1. And in terms of, well, it's not exactly negative 1. it's infinitely close to -1. So given that we're just computing limits, for our purposes, it is that way. A more rigorous approach to this problem would involve sequences and or delta epsilon definitions, in which case we would get a result that would be equivalent to us saying this is -1. So to save ourselves the hassle of a more rigorous approach, 2 from the right minus 3 is -1. Now, on the bottom, if we have x approaching 2 from the right minus 2, this represents a number that is slightly greater than 2 minus 2. So it's almost 0, but because it's a number slightly greater than 2 minus 2, it's slightly positive. Now here we've got a negative divided by a positive, which is negative, and 1 divided by 0, if it's a one-sided limit, will go to infinity. Now again, as we found out from earlier, in order to have 1 divided by 0, it's got to be 0 plus or 0 minus. We can't just say 1 divided by 0 because that could be positive or negative infinity, and that means the limit might not exist. Okay, and then there's problem 3. Well, with problem 3, as much as it's squared, a number slightly more, so 5 squared is 25. A number that is slightly greater than 5 squared will be slightly greater than 25. Hence, the bottom will be 0 positive, because it will be almost 0, but it is slightly positive because we're taking a number that's slightly larger than 25 and subtracting 25. So we will have a small positive margin left over. On the top, we have 7. So now we have a positive number divided by a positive number, which gives us positive infinity. Okay, so now we have two-sided limits which may or may not result in infinity. I say resulting in infinity just because this is the topic that we're on for this series of lessons. However, I'll give you a full-on hint. These limits need not result in infinity, because otherwise, well, sorry, it would make it be boring. Maybe easy enough for you that it wouldn't be boring. However, sorry, if you want something really easy, if college was too easy, you wouldn't gain much from it. Yes, hate me for that statement if you want to. Sorry. Okay, now, think about it. What do we need to do to check whether a two-sided limit even exists? We went over this a couple pages ago. By the way, yes, originally these were PowerPoint slides, so you could say a couple slides ago. Okay, so for a two-sided limit to exist, we have to check the one-sided limits if it's ever a function with a discontinuity. And any function that has a 0 on the denominator has a discontinuity. So immediately, for all three of these, we have to at least consider one-sided limits if we can't simplify. And for 1 over x minus 7, there's no way of simplifying that. So that means we have to split it up, and we have to check the limit as x approaches 7 from the left of 1 over x minus 7, and the limit as x approaches 7 from the right of 1 over x minus 7. So, from what we did earlier, plugging in 7 from the left into 1 over x minus 7, so that would be 1 over 0 with a minus sign, which is negative infinity. On the right, plugging in, that would be 1 over 0 with a plus, which is infinity. These are not equal. So whenever the right-hand limit does not equal the left-hand limit, we have to say the limit does not exist. So the limit as x approaches 7 of 1 over x minus 7 does not exist. So that now brings us to the second. So the second two-sided limit we're going to consider is the limit as x approaches 9 of 1 over parentheses x minus 9 parentheses squared. Given that there's only a single number on the top, there's no meaningful way to simplify this. Any way of modifying this fraction is going to result in more writing and isn't going to do us any good. So again, given that we can't simplify this, we have to go with one-sided limits. So again, we split it up. So we have the left-hand limit, 1 over x approaches 9 from the left, 1 over x minus 9 squared, and the right-hand limit. Limit as x approaches 9 from the right of 1 over parentheses x minus 9 parentheses squared. So going ahead and doing the computations, so this is 1 over 0 minus squared. Negative times a negative is a positive, so that's 1 over 0 with a plus. So that's positive infinity. Then for the other one, this is 1 over 0 with a plus squared. Positive times a positive remains a positive. And that's also positive infinity. So the left and right hand limits are equal to the same number. So that gives us limit as x approaches 9. Whoops, need to draw an arrow there. So limit as x approaches 9 of 1 over x minus 9 squared is equal to positive infinity. Okay, now take a look at the last one. Before we go through this, I want you to identify not only how this is different, but I want you to think about what happens when you try to compute this. Because this last one has a major difference compared to the other ones. And yes, I did give a hint at it. If you want to say I made it anticlimactic, go ahead and blame me. Just by the way, please don't take your anger at me out on your screen. You know, that doesn't do anything positive, only negative. Nor take your anger out on anything in your house. If you want to wait until we get back to chew me out, you know where I'll be. Okay, so if you look at the last one and you plug in, unlike the other ones, we get 0 over 0, which now we don't just have a number over 0. So this is a true indeterminate form, meaning it could be anything. Now the other thing about it is with this one, the top isn't just a number. Instead, the top is an algebraic expression. It's a binomial. And so that means there's a chance that we can simplify. Now, the bottom is a difference of squares, and a difference of squares is going to be a plus b, a minus b. In this case, A is x, and b is 5. So factoring the bottom, we get x plus 5 and x minus 5. And then the top is x minus 5. And remember, you can always write that as 1 times whatever you have. So now we can cancel the x minus 5's, and we're left with a limit as x approaches 5 of 1 over x plus 5. Well, now plugging in, that gives 1 over 10. And in this case, that's a real number. That's the answer. We're done. So a key thing about this is just because the bottom is 0 does not necessarily mean it's going to equal infinity. You can still look to simplify in the cases where that's possible. It's not always possible. So that's the end of this lesson on infinite limits and limits resulting in infinity. I thank you for watching this, and if you have any questions, you are always welcome to email me or come by my office. Thank you, and have a happy Thanksgiving.